Alright, so in this video we're talking about two-way tables and conditional probability. So starting with two-way tables, there's a couple of definitions that we need to be aware of. And the first is a mutually exclusive events. So mutually exclusive events mean that the events have no outcomes in common. Or another way to word this is they can't happen at the same time. At the same time. So an example of this, say we have a dice and we roll it. We can't roll an even number and roll an odd number at the same time. There's no even numbers that are also odd numbers. So this is an example of mutually exclusive events. The second definition is overlapping events, which you may guess is kind of the opposite of what a mutually exclusive event. This is, they do have outcomes in common, and they can occur at the same time. At the same time. Okay, this is super important when we're finding intersections because we want to make sure that we don't count things twice if they're overlapping. So an example of this would be rolling an odd and rolling a number less than 4. Those are overlapping events because there are odd numbers that are also less than 4, like a 1 or a 3. So if we rolled a 1, we'd be rolling an odd number, and if we rolled a number less than 4, we'd be rolling an odd number. So those events are overlapping. And as we talk about it, as I go through number 3, we'll kind of talk about this a little bit more and why that's so important. So first we need to fill out this frequency table. So we start with 80 children went on a school trip. So our total number of children, which ends up right here, is 80. And then 23 boys went to London, and 19 girls went to London, and then 14 boys went to York. So now it wants us to use this information to complete the two-way table. So you kind of have to just look through and see what you have enough information to figure out. Like right here, I have 23 and 19, so I can figure out the total number of people who went to London by just doing 23 plus 19. So 23 plus 19 equals 42. Sorry, there's people knocking at my door. And then I can figure out how many went to York by there's a total of 80, and then I subtract the 42 who went to London, and 38 went to York. And now I have enough information right here that I can figure out how many girls went to York because there's 38 total, 14 boys. So if I do 38 minus 14, I have 24. And then I can find my total of boys and girls by just adding straight across. So 23 plus 14 is 37. And 19 plus 24 is 43. And I can kind of check to make sure I did that right because 37 plus 43 is 80. So everything added up the way that I wanted to. So now I'm going to go ahead and find some different probabilities using this to explain why this overlapping event thing is so important. So I'll start by finding an intersection. So let's find the probability of boy intersection York. So we'll remind ourselves what this intersection means, and it means and. So the probability that we pick a boy that and went to York, so the person we pick is a boy and they went to York. We come here and we go to boy and York, and we have 14 total out of 80 possible students. So that's 14 out of 80. And if I do that dividing, 14 divided by 80 is 0.175, which is 18%. So that's fairly straightforward. The one where this overlapping events really matters is actually with the union. I think I might have said intersection earlier, but it matters with a union. So let's look at a union. Let's have the probability that it's a girl union with London. So reminder of union means or. So this is the probability that we pick someone who's a girl or someone who went to London. So we have 43 girls total, and we have 42 that go to London. Now here's the part where this overlapping events really matters, because these 19 girls that also went to London, so they're a girl and they went to London, we've counted them twice because we counted them in this 42 and in this 43. And so that's going to kind of mess up our numbers. So we need to subtract one of those out. So we're going to do 43 plus 42 and then minus that 19 so that we only count it once instead of twice, and divide that by our total of 80. So if I go ahead and put that in a calculator, I have 43 plus 42 minus 19 is 66 divided by 80 is 0.825 or 83%. And that's pretty much the most complicated thing that I'm expecting you to do using two-way frequency tables. And I don't think intersections, I don't think you'll have any trouble with. And the only thing to remember when finding a union is to make sure that you don't count things twice. So since this 19 was counted in London and girls, we'll subtract it once to make sure that we don't double count things. The second thing we're talking about today is conditional probability. So I'm going to flip over to a new document really quickly. So conditional probability is a little bit different because we're used to always dividing by the total. And the conditional probability, we don't have to do that anymore because we know something about whatever we're given. So here's an example. We have this nice two-way table here, and there's an online ad encouraging people to plan New York vacations. And we want to know, okay, if they watch it or if they don't watch it, does that change the effect on whether or not they actually plan a trip to New York? So the first question is, what is the probability someone plans a vacation to New York if they watch the online ad? So this is telling us right here they were only worried about the people that watch the online ad. So we're not worried about these people that did not watch the online ad. We're going to just ignore them for a minute. So we don't really care about our total either because we just care about people who watch the online ad, which is just this top part. So what's the probability that they do plan a vacation? They plan a vacation. So that's this number out of our total number of people who watched the online ad. So to find this probability, we do 300 divided by 750. So 300 in my calculator divided by 750 is 0.4 or 40%. Okay, and then what's the probability that someone plans a vacation to New York within a year if they do not watch the online ad? So now we care about something else. We care about people who did not watch the online ad. So we're going to ignore the people who did watch the online ad and just look at those who did not watch the online ad. But we're still looking at plans a vacation, which there was 100 who planned the vacation who did not watch the ad out of a total of 250 people. So we're going to divide that. 100 divided by 250 is 0.4 or 40%. So then our last question asks, do you think this ad works? Why or why not? Well, it seems to not matter whether or not they plan a vacation or don't plan a vacation, depending on whether or not they watch the online ad. So I would say the ad does not work because it has no effect on whether or not they end up planning a vacation. So because these percentages are the exact same, regardless of what happens, we're going to say the ad does not work. And when that happens, this means that these two events are independent of each other. Okay, so let's talk about conditional probability if we don't have a two-way table. All right, so this time we're given some information that's not in a frequency table. So we're told we have 3 blue marbles, 5 red marbles, and 4 white marbles. So if one marble is drawn at random, we're going to find these conditional probabilities. So this is red, the probability that it's blue, given that it's not white. So we only care about the marbles that are not white. So we're going to ignore these and just look at these two. So the probability that it's blue, so we have 3 blue marbles out of, if we add our 3 and 5, we have 8 total that are not white. So 3 out of 8 is our probability that the marble is blue, given that it's not white. And again, if we put that in a calculator, that equals out to be 38%. So then we'll look at the second one, the probability that it's not red, given that it's not white. And so again, we're ignoring our white marbles, and we have the probability that it's not red. Well, if it's not red, it has to be blue, because those are the only options, and there's 3 blue out of 8 that are not white. So these are actually asking for the same thing, just using 2 different ways of asking. And then our last example is the integers from 10 to 50. So the first one's asking, find the probability that it's even, given that it's greater than 40. So if we think of our numbers greater than 40, those are the numbers 41 through 50. There's 10 total numbers that are greater than 40. And so we know this is going to be out of 10. And then the probability that it's even and greater than 40. So we have 42, 44, 46, 48, and 50. So there's 5 numbers that are even, that are greater than 40. So we have 5 out of 10, which is 50%. The second one asks for the probability that it's greater than 40 and it's even. So we have the numbers 10 to 50, so there's 40 total numbers. And the probability that it's greater than 40, well, we just talked about that up here. They're 41 through 50. There's 10 numbers greater than 40. So the probability that it's greater than 40, given that it's even. So 40 was our total numbers. So if we only look at the even numbers, that's half of that. So there's 20 even numbers. And then greater than 40, we only care about, there's 10 total, but we only care about the even ones. So there's 5 that are even. So we have 5 out of 20, and if we divide that, we're at 25%. And the last one is the probability that it's prime if it's between 20 and 40. So we're going to say that this includes 40, does not include 20, just because between is kind of a hard thing to decide what that means. So if it doesn't include 20, includes 40, there's 20 total numbers from, if I count from 21 to 40. So then I've just got to count my prime ones. So I'm starting with 21, 22, neither of those are prime. 23 is prime. And we can only have to worry about odd numbers since even numbers are never prime. So 25 is not, 27 is not, 29 is, 31 is, 33 is not, 35 is not, 37 is, 39 is not. So we have 4 total prime numbers that are between 20 and 40. So we have 4 out of 20. And if we go ahead and divide that, we're left with 0.2, which is 20%. So that's just a reminder on how to find conditional probabilities.